we're just going to do a few examples, okay? This is a short session just to practice drawing the graphs and calculating the energy. Now, you'll have seen, and we did go through it in previous, and we spoke about it before, you'll have seen that there's a table where they give us bond lengths, bond strengths, bond energies, or whatever the case might be, okay? From there, we can start looking and working out some of the endo or exothermic properties of various reactions. Let's take our favorite reaction over here, nitrogen gas plus hydrogen gas, okay? And that's going, I'm using the double arrow for a particular purpose, to an NH3 gas over here, and we've got a 2 and a 3. Now, if you go to your, if you go to this sort of the general tables that you get, I've got one in this book, for example, where they have got the bond energy tables, and they're kind of like give you a whole list of different kinds of reactions, and they're shown like this: a CC, an N bond. So, and they've got energies associated with it, usually given as a bond energy as a number. Okay, and the numbers you get, remember we spoke about it before, kilojoules per mole. Okay, let's have a look here. What are we going to break up? So first of all, let's just put in our sort of wall over there again. This side is going to be the breaking up, okay, of bonds. This is the, I don't know, let's call it making up. Okay, all right. So on the breaking up side, what have we got? We've got to break up an N2 bond, right? So we've got to break a nitrogen and a nitrogen. So we go to our bond energies and we say, right, nitrogen, nitrogen, and we have a look here, and I've done those already. So we look at nitrogen, and it's 941. I just want to double check myself. Okay, some of them give 946, some give 941. All right, it doesn't really matter. Okay, whatever book you've got, it's 900 and something. Okay, let's say it's 940. Let's say 941. Okay. Then what have we got to break up? This is kilojoules per mole. All right. Then on the other side, we've got to break up hydrogens, but we've got to break 3 of them. So the energy per hydrogen, check my table, the hydrogen is 436. Okay. So that one, that's that. To break up one HH bond is 436 kilojoules per mole, and we have to break up 3 of them, so we end up with a total of 3 times that, 1308 kilojoules per mole. So therefore now we say, right, total energy to break is going to be what? Well, the total energy to break them is going to be the 941 plus the 1308 gives us 2249 kilojoules per mole. Okay? Then, well, what have we got to make up? We've got to make, can you see there? We've got to make 3 of those NH bonds. So we look, an NH bond is 389. So to do one of these bonds, okay, just to do one, there is 389. Okay, this is, remember, this is the energy given off. So this is now given off, right, during the process. So what have we got here? We've got 389, but now we must multiply it because there's 3 of them. And 389 times that is 1167, right? Kilojoules per mole. But now bear in mind, that there, just to go back to this, right? Remember what we've done here is this. Okay? That was 1. Was the 389 was given off when that joined. So when that electron went in and went into that parking spot, 389 was given off. There's another one going in, right? And there's another one going in now. So what have we got here? we've got 3 of those bonds. So hence, each one is going to be 389 times the 3 to give 1167. But that is only for one molecule. And we make 2 in this process, right? So therefore, the total energy given off, we have to say, well, times 2. It's this number here, isn't it? Right? The same as we did for hydrogen, we had to break a total of 3 hydrogens apart, didn't we? So therefore, we end up with a number there of 2334 kilojoules per mole. Right? Therefore, what do we do at the end? We do our little energy balance, and we say, right, energy there, okay, less energy there. This is the energy that it contained. Remember, okay, we broke the bonds, that's what we put in. So what are we doing now? We take it off. So in was 2249, out was 2334. So we go 2249 minus 2334, and that gives us a total of 800, let's just have a look here. 2334 minus 2249 is going to be equal to 85 minus 85 kilojoules per mole. Okay? Which means it tells us straight away that this reaction is exothermic. Right? Let's do another one of these. Okay? Let's take this one. We say, all right, H2 plus Cl2. Okay, we're going to make H2, H2, gas, obviously, plus Cl2, gas again, and that's going to 2HCl. What are we doing? We're manufacturing hydrochloric acid, right? So now what do we have to do? We draw a line there and we say, right, this is breaking up, and this is making up. Okay? Could be an apt way of looking at it, I suppose. So how much energy is required to do an H2? Well, in other words, to pull one apart is we require 436 kilojoules per mole. To break a chlorine apart, okay, we require 243 kilojoules per mole. So if we add those, that's the total energy that we need to put in order to break this lot up, isn't it? Okay, it's to get us a broken up situation. Then what do we say? We say, right, let's add them 679, okay, kilojoules per mole, okay, and out is an HCl. So let's just say, right, hang on, let's do it as red, okay. We've got an HCl bond. How much is that? It's 431 kilojoules per mole. But we must form 2 of them now, right? There. And that's going to be then 862 kilojoules per mole. Okay? So we take in versus out, and we end up with, let's have a look, we've got 697 minus 862 is going to be minus 165 kilojoules per mole. Okay? So once again, that's going to be an exothermic reaction, isn't it? Okay? It's going to be exothermic. Well, let's have a look in life at where this impacts us, right? And a very nice one was in one of the textbooks. Okay, as I say, I'm trying to use everybody's textbook. Okay, so that there's overlaps between it, because obviously, I mean, everybody's going from a different point of view. But by trying to do and use bits and pieces from everywhere, including the internet and some A-level stuff, we can try and build up a whole lot of different sort of sets of looking at the thing, right? So let's have a look at an exo and an endothermic reaction. Let's have a look here at respiration. Okay? This is really a great example. Respiration, I'm going to use the formula C6H12O6. C6H12O6, okay? And it's got here as a solid plus O2. 6O2 is going to go to 6CO2. Let me just take this down a little bit so I can. 6CO2 plus as a gas, okay, plus 6H2O liquids. All right. So this, what have we got on the respiration side? What are we doing? This is a basic sugar in its simplest form, isn't it? So what we've got here is we've got sugar, okay, plus oxygen, okay, and I know I haven't put the 6 in there, right, is giving us CO2 and water. Right? What are we actually doing? Remember in I think it was grade 9, maybe even a little before, when we started talking about chemical reactions, what did we say? We said in the presence of oxygen, that's how we say it's burning. So what are we doing is we're burning sugar in our bodies, right, as we inhale and exhale, right? So the sugar's being burnt up in the bodies in the presence of oxygen, it's broken down, right? The breaking down process, okay, gives us CO2 and H2O. But more importantly, okay, this reaction, I mean, we're not going to work, but you can. You know, if you've got the tables, work out the 6, the H12, and you can work out how much it actually physically is, right? What have we got here? We've got, this one is, we know that energy is given off. This is an exothermic reaction. Okay? Because the energy given off is our, I'm just going to use life force if you like. Okay? It's like a life force over there. Okay? Now, that's what we're doing, isn't it? We're breaking sugars down. Depends, it doesn't matter which one is fructose, sucrose, glucose. Okay? We're breaking them down to give us the energy that we need to continue. I mean, obviously, there's other things and other ways it's broken down as well, carbohydrates and things like that. But basically, what we've done is burn sugar to give us energy. That's the exothermic reaction. It's given off and our body uses the energy, right? What is the reverse of this? Well, the reverse of this, for those of you who are doing the life sciences, would be photosynthesis. Because in photosynthesis, it's exactly the opposite, right? What happens in the opposite one is you've got the energy, okay, photosynthesis. What happens over here, okay, is we have sunlight. What is sunlight? It's energy, right? Okay? Those of you who don't believe, go and stand in the sun with on a very hot day and see what happens. The energy comes in, doesn't it? The energy is absorbed by the plant, right? The plant uses that energy in the reverse process, okay? It manufactures the sugars. It goes in reverse. That's what photosynthesis is in the simplest form, right? So, yes, what have we got here? We've got a situation where we've got an endothermic reaction. All right? Simple as that. Right? You can extend this to all kinds of things that you like, essentially, right? You just look around, look at some of the things. Think about ice cream, for example. What do we do when we create ice cream? We actually take heat away, don't we? We remove it. We freeze it, essentially. We remove the heat from it. Okay, well, that's great. Well, then what happens when you take the ice cream out of the fridge and you eat it? You apply heat to it, doesn't it? The heat adds energy to the molecules that are moving, and by adding energy, they start to melt, right? There you've got your endos and exos as well, right? It's in everything we do. And the concept here that we just need to finish off on is or the concepts that we need to talk about, okay? First of all is just to introduce a reaction that's reversible, all right? I think we've discussed it before, just basically. But just take, for example, where we've got water, right, is a liquid. We add heat to it, and we get water, which then goes to a gas, which is steam, right? So in a kettle, we've got the water, and it starts to boil, right? We add heat to it. Then, if you look carefully at, if it's a glass kettle, right? If you look carefully, you will start to see the steam eventually forms little drops of water on the side, right? And what is happening here is the H2O as a gas is going back to H2O as a liquid, isn't it? Right? So this reaction is reversible. I know we've mentioned this before, but the concept of a reversible reaction is important because in the processes we're going to look at where we're manufacturing certain things, we are able to move them backwards and forwards. So we can combine hydrogen and nitrogen to form the ammonia that we've been doing. We can combine H2 plus I2. H2O gives us hydrogen iodide, right? There's various things we can form. I think HF is hydrofluoric acid. So we can form many different compounds. But the beauty is that that compound can be reversed. So if, for example, it's forming the ammonia and our tank is full, we can stop it by doing something to make it reverse. This is the concept of equilibrium that we need to talk about. The other element of this is the use of a catalyst, okay? I mean, we've all heard of the term catalyst. Catalytic converter, right? Anybody who's done projects, and I'm sure you've all done projects on global warming, it's obviously the topic of the decade, an important topic for the future, yeah. But in this process, right, of looking at this, you've heard of this catalytic converter in an exhaust of a car, right? What is a catalyst? It's actually something that we put into the chemical reaction, okay, that just speeds it up. Because you can imagine some reactions can take a long time, right? But if we put this catalyst in there, we are able to get it to go faster, right? If we can get it to go faster, that means that maybe it's a better, cheaper option, right, to put the catalyst in. Now, the secret of the catalyst, or just one way of thinking about it, is let's go back to our atom, our NH4. Here's our nitrogen, remember? Now, nitrogen has got 3 parking spots, right? There's 3 electron bays in the outer shell over there, right? The valency is -3. Therefore, we're getting 3 electrons coming in there. But hold on, we've heated this stuff to break it apart from its mate, the other nitrogen, haven't we? So this thing's got increased kinetic energy, because what is a temperature measure of? It's a measure of kinetic energy, isn't it? We've added temperature, so we've made this guy whiz faster. Now we're saying, hello, we're going to park an electron in there. Would you please hold still? No, he's not going to do that, is he? So we've actually created a situation by breaking this that's made it more difficult for this electron to come and say, hold on, and park an electron over there. But now we're going to get 3 electrons parked in there, okay? They're tiny, and the parking space is tiny. We're talking electrons here, guys. So we try, it's like it's beyond needle in a haystack stuff, isn't it? It's like that piece of dust that's flying over Europe will land on my nose in the next 2 hours. Okay? It's ridiculous probabilities if you think about it, right? So what does a catalyst do? We put a catalyst in, right? And just think of it in this term. The catalyst says, hold on, and it grabs the nitrogen, slows it down, okay? The nitrogen's now slowed down. He's also pointed with his parking bays pointing up like that. So now it increases the chances of the hydrogens bonding in. And when the hydrogen's got its 3 electrons bonded in, the catalyst releases it and lets it go. Okay? So it's essentially, it's like a glue, if you like. All right? But the secret is the catalyst doesn't get used up. Okay? Nothing essentially happens to it. We're just using some of its properties. And you're going to come across a whole lot of different things that can be catalysts, right? Depending upon the reaction, depending upon the chemicals that are being used, it dictates the kind of catalysts that we need to use for that specific reaction. Okay? So essentially, those are the concepts that we've got to deal with. We've now covered most of the energy, the exo, the endothermics. We've spoken about the catalysts, right? And the concept of a reversible reaction, right? We're going to move on in the syllabus now, and we're going to start looking at the concept of an acid and a base. I know we've looked at it before, but we're going to look at it in a little more depth in the next session, because what we want to do is we want to understand how it actually forms and how it does what it does do, all right? Because remember, these are some of the basics of the building blocks that we basically live by, right? Acids, lemon juice, vinegar, right? Pool acid, okay? Different things. And also the concept of the strength of an acid, okay? The thing that you've heard about, the pH and things like that. And obviously, how do we know if it's an acid there or if it's an alkali or a base? We don't know. That's what we're going to start processing and probing in the next section.